Hi, folks. Welcome to Percona Live. It's glad to be here, and it's great to see all of you here. I shout because I do not feel so comfortable in front of the camera, so I hope everything goes fine today. Let's start. Here we are. Today's talk, we're talk about how we can reduce cost and improve performance with data modeling on Postgres. Well, first things first, my name is Charly Batista. I'm a support engineer here at Percona, and I've been working with Postgres and database for more than 20 years right now. And I'm Brazilian, and I'm living in China for the last like 6-7 years, I guess. And you can find me at my LinkedIn profile that you can see here. Or if you would like to, you can also drop in an email. My email is going to be by the end of this presentation. This is going to be our agenda today. We'll have major 4 sections, a quick hardware review. That's going to be really fast, really quick. We're going to see how Postgres stores data, how Postgres manage the stored data, and how those can impact our wallet, because, well, this is what this presentation about, right? How we can reduce costs. I want to start with a disclaimer here. This presentation is not about modeling database. It's more about Postgres internals, I would say. This talk is going to be about how Postgres stores and organize the data internally, and how we can try also to understand how the different data types can influence the data growing when we are storing the data, and how we can make those same data types occupy less space without changing them during the modeling process. We'll also try to understand how Postgres manage the free space inside the tables, and how it knows what needs to be cleaned or not using vacuum, for example. And at the end of this talk, we should be able to understand how our decisions that were taken in the past, when we were modeling our database, they can impact the storage cost that we're having now. And more important, how we can try to minimize those impacts and make the cost smaller. Well, let's start. As I said, we'll have a brief hardware review here. And we're going to start our discussion taking a look on the main memory architecture model that you have nowadays. And if we see here from the top down, everything starts inside of the CPU. Everything starts on the register. And then we have the cache memory, the main or primary memory that we usually call them. And then that we have the auxiliary memory. And it's important to understand that as we go to the top, the performance improves, but also the cost improves. The more the bottom, the less the cost, but also the less performance is the storage that we have here. And one very important thing that we need to keep in mind, and that's going to be important to our discussion here, is that CPU doesn't have directly access to the auxiliary memory. It means that everything that is on the hard drive, on the hard disk, it's not directly accessed by the CPU. It needs to be copied from the secondary memory to the primary memory. Then the CPU can access, and CPU can work with that information. And this, bear this in mind, because this is going to be very important to our discussion here. Well, moving on. The memory architecture from a persistence perspective, it's either volatile or non-volatile. Main memory is volatile, and it means that if we lose power in our computer, everything that is on the main memory, it's on run, it's gone. That's it. And for the other hand, secondary memory is non-volatile. So that's why we use those slow devices to store the information, because we need them to persist, and we need to keep that information. Main memory is usually much faster than the secondary memory, but it's very expensive. Well, for the other hand, the secondary memory is usually cheaper, but it's much larger. And it's pretty slow, as we all know. Accessing the hard drive compared to access the memory is a very slow process. From the access perspective, memory can be either randomly, sequentially, or directly accessed. For this discussion, this talk here, we are not interested in direct access. We're only gonna talk about random and sequential access, and we're gonna see why this difference is important and why they made a lot of influence on the database designs, on the storage designs from the database. One thing to note is that data can only be written and read from disk in blocks. We cannot access a disk device that's also known a block device to read only 1 byte of information or 1 kilobyte of information, let's say, on this way. We need to read or write a block of information. And most of the operational systems, they are designed to work with block of 4 kilobytes. And we'll see that the Postgres, it works a different block size. It's a multiply of 4 kilobytes. It's 8 kilobytes, we're gonna see later, but it still works with blocks. So we cannot access either a single row or single piece of information on Postgres or any other database. We need to access the whole block. And that's also important for performance perspective. And we're gonna say later. Data can be stored randomly or sequentially. This is also another important piece of information. And why is this important? This is important because, as you can see here on this picture, on this diagram, the random data, it means that it's stored on blocks inside of the device that may be far from each other. So if we remember how spinning disks work, for example, on a spinning disk, it has a spinning and rotating platter. That's why it's called spinning disk. It also has a head that is moving from on top of the platter to find out the information. So if the data is sequential, the time it needs to be read is just the time that the platter is spinning, is rotating. So it can be really fast. If the access is random, if the data is randomly written, then the head needs to move on and back on top of the spinning disk. And it makes the access to the data pretty slow. This is what we call seek time, when the head is moving on the platter of the disk to find the correct position that it needs to be in order to start reading the information. And it makes the spinning disk a lot slower than when doing random access than sequential access. And that's why most of the system, most of the database and the systems, they try to keep the memory, the information, as sequential as they can. Some of the database, they use an in-memory strategy. What they do, they put most of the data in memory. When we're changing a tuple, for example, when we send an update to the database, instead of just getting this data and updating and writing back to the disk, it keeps there in memory because it can have other tuples that is close to that one that was updated, or it can update this tuple again. So if we get a lot of updates that was being done randomly on the time, and we keep it in memory, we can make it sequential. And then when we write down to the disk, when we flush to the disk, we just flush that whole sequential information to the disk. And we make a random access device, that's a spinning disk, for example, just to look like a sequential access device. It's why it's so important that we have that space in memory to keep the database fast. It's not just because memory is faster than the hard drive, but we can use this speed up on memory to make everything looks like sequential. instead of just making a lot of random access. And this, for spinning disk, it can give an improvement of 10 or 100 times. It's like an order of magnitude. And that's what we can see here. This is just a brief comparison between the performance on a spinning disk on a ADDD device when we have access compared to random, when we have sequential compared to random access. So for the same amount of information here, let's say we want to put here 1,000 blocks of 8 kilobyte blocks on a spinning disk. If we do a access, sequential access, we just gonna spend 6.1 seconds here on the device. Well, that's not bad, right? But if we do, I mean, if we do sequential instead of random, this is what's random. If we do sequential instead of random, we can drop from 6.1 seconds to 53 milliseconds. Those are order of magnitude improvement on the access for the same size, for the same 1,000 blocks here that we have, just making them accessibly sequentially instead of randomly getting those information from the disk. If we do the same comparison using an SSD, and we're going to see that the performance gain is not so huge. So we drop from 43 milliseconds. So well, it's not that huge if we compare back here with the spinning disk, but we still have a gain, and we're still doubling the time when we have random access instead of sequential access. There are a lot of research being done to improve those time, to improve those performance, but if we can still keep them sequential, like using strategies like the one I've explained, we can get a lot of performance improvement, and without changing much on the database. Well, let's now start talking a bit about Postgres, how those things work on Postgres. The first thing that we need to understand is how Postgres stores the data internally. There are many different strategies to store data when we go to physical device, when we're talking about the file, the physical file itself. We can have a heap file, like how Postgres does. We can store the information in cluster index, like other database they do. They implement a clustered index storage. So, but Postgres, it does use a heap file, as I'm saying here. And what is important is to understand is that heap file is one of the simplest form of organization inside of the hard drive. So a heap file is just a collection of blocks that are put one after another. So there is no special thing about heap file. It's just a file with a band of random information that is stored there. So a heap file, it stores data in blocks that we also call pages. Remember that the hard drive, the disk, it stores the data in blocks, right? So the heap files, it just keeps this type of organization. It stores in blocks. The store is not order. There's no really order, and we cannot expect any order that when we're working with a heap file. We'll see there are benefits and also drawbacks for this strategy. For example, if we compare how we do a full table scan or how we traverse the heap file, it's way more efficient if we compare with another strategy. For example, when we use cluster index. When we use cluster index file organization, we need to traverse using the queue order. What is a cluster index or a cluster file organization? It's a file that is organized, is ordered on using a key. Most of the times, most of the database, they use the primary key because it's more efficient to organize the file. So everything that's stored on a cluster index is organized on the key order. And the implication of that is if we need to traverse, if we need to read the whole file, the whole table that is inside of our cluster index, we cannot do it physically. We cannot traverse it physically because it needs to be done in the key order. And in the key order, they are not necessarily close to each other. They're not necessarily next to each other. But in the heap file, because you do not have any order, all the blocks, they just put one on top of the other. So we keep the physical order on the device. If we need to traverse, if you need to read that file, we just ask for the device to get the file, and it will do, and we just go from top to bottom and read the file. That's just pretty fast operation to be done when we are using a heap file. And that's one of the most advantage when we compare a heap file to cluster index strategy, for example. Another thing is some operations, they're not really done physically when talking about heap files. For example, there is no real deletion on heap file. When we need to delete or to remove a record, we just go there and mark that record as removed. It's a logical deletion. So, but the record is still there. It's still occupying the space. We should implement a method, we should implement something to go there later on and remove and make that space available. But the record, the row is not really deleted. It's not really removed. It's still physically there. It's just marked as removed. It's just a logical deletion. An update does a similar operation. When we need to update something inside of Postgres or a heap file, it goes there, mark that item as removed, and then just insert the new record in the end of the file. And one thing that it does is it can improve performance. Remember that I said some database, they try to keep the information on memory as the more they can, because if that information is updated, is changed, it can just concatenate one after another and make it look sequential on the disk. Well, this is one of the ways, it's one of the methods that it can be done. So if we need to update in place a lot of records, let's say I send an update to my database and it does update 10 rows. So it needs to go to the 10 rows, read those rows, change and write back again. If they are in different pages, in different blocks, the disk needs to go in back like in many different positions. And when we remember about how spinning disk work, that's very inefficient. So if we cluster them together, if we concatenate all those chains, all the operations, and then just flush them in one batch, that's a much faster operation. And how it works on Postgres. The heap file in Postgres, they are implemented using 8 kilobytes page. So we do not, Postgres doesn't use the page size as most of the OS they do. It use 8 kilobytes page. It can be changed, but it cannot be changed online. Actually, it needs to recompile the database to change. So if for whatever reason we need to change the page size of Postgres from 8 kilobytes, 16 to 32, or even to 4 kilobytes, we need to recompile the database. Also, Postgres puts a limit on the file. A heap file on Postgres has a limit of 1 gigabyte. It doesn't mean that the table has a limit of 1 gigabyte. The table can grow even more than that limit. It means that if the table grows for more than 1 gigabyte or terabytes, let's say, for each 1 gigabyte data that's stored on that page will be created 1 heap file. So for the same table, the same logical table on the database, we can have a lot of smaller files inside of the disk of 1 gigabyte size, each of them. And a very important concept is that different from other types of organizations like cluster index that I've mentioned before, is they are stored close to each other, as I said before. So when we have a block on Postgres, and we'll see here just in a moment, all those rows, they're just put one after another. And as I explained before, it's very important to make access to them faster when we need to go to the disk. We're gonna have a few demos during this talk. Some of them I'm gonna do in place here, like for example, we are just checking the heap files now, right? So if we go here, let's just do some configuration here. Not folks, that I'm disabling auto vacuum here, right? And I'm doing that because I need the Postgres to do not change anything that we're doing in place here. So a disclaimer: never ever do this in your production database. Never disable auto vacuum in your production database. This is a topic for another talk, but if you believe or think auto vacuum is doing something that is not necessary to be done, so there might be some configuration problems or something that needs to be reviewed. But auto vacuum is a very important piece of software, and that needs to be run on your database. So again, never disable auto vacuum in your database like I'm doing here. So let's say, yeah, it's off. All right. I'm gonna create a couple of tables here in this database. So I'll make sure that the table doesn't exist. I'm gonna create it again. It's a very simple table. We have one integer, one text, one decimal here. So I put this order here because we can see clearly how the test is gonna appear later on the file storage. So I'm gonna insert like 1,000 rows. I want to make sure this data is sent to the disk, so I'm gonna do a checkpoint here. I need a couple of extensions to be able to inspect it inside of the database. So that's why I'm creating here those extensions if they do not exist. In my case, they already exist, so they've been created. I want to see what is my data due. So this is my data due. I'm copied here already. And Postgres, it doesn't save the files using the name of the objects. So what it does, it has an internal identifier, an internal object identifier, and it uses the object identifier to save the files. And that's why I need to get it here, because I want to access from the file system perspective. So I'm getting here, this is the name of my database inside of the file system. And this is the name of my table inside of the file system. So I've been dropped, it's been changed, so I need to replace here. And if I go here to my file system, I can now change these parameters, and okay, I go to, this is my database folder. If I check here, I'm gonna have a lot of files here. So those many files are for other tables and others that are inside of this database. But the ones that we are interested in is just this one here, right? This is the table that we want to check. This is the table that we've just created. So it has 56 kilobyte in size. And we can inspect this table using an XDAMP tool. And this is how it looks like inside of the file system. Well, it doesn't look nice, right? So it doesn't look pretty. The thing is, we have a lot of header information here. We will see what they are. But if we keep moving, at some point, we're going to see our data. This is how it looks like. So see, all the data is sequential, and even though it looks like there is an order here, it's just happened that when we inserted, the database just put them sequentially, and because I've just inserted them sequentially here, they are keeping this order. But we will see later on that we cannot expect that any order will happen here on the database. And this is it looks like inside of the database. So moving on, how a page is organized is divided inside of the heap file. As said, the heap file is organized in pages, and the page itself, it has its own organization. So the page is divided basically in a header, as we saw here. So if we go to the top, we have a header here, and after this header, we have pointers, what we call line pointers. Those pointers, they don't really hold the data. This is not where the data it is, but it points to the data that are those tuples here in the end of the page. So we have the pointers, and then in the end of the page, we have the data itself, the rows. So these are, and in between of them, we have a lot of free space, empty space. So it means that how it works is the line pointers, they grow in the direction to the center, and then the rows, they grow also in direct to the center. And why Postgres doesn't store the data here? Why does it need to have those line pointers here inside of the page? So it's here because it makes it very it makes Postgres to do not really depends on the physical location of the row. Remember that I said the Postgres doesn't really update the row that is in place here. Let's say if we have an index, and in the index, because Postgres doesn't store the index inside of the page itself, the data itself, the index needs to point to the row location. So if we update an index, when you create an index, the index will have this location here, the location of this pointer. When we update an index, a row, so this row want to change for another location. Let's say the row is this last one. We update, and then the Postgres just insert a new row, is this new tuple here. See, the position is changed. If we do not have these pointers here, we need to go to the index table, to the index file, and update that position in the index file. But because we have this pointer, this is just a pointer to the position where the row is located, we can just update the pointer here to point to the new location. We don't need to update the index. We save this operation. This makes it faster. So it's a very powerful design that we can use to improve a lot of performance when we're working to the database. We can save a lot of access to the storage device. All right. We can inspect how it works, and we'll see later how it works. But the page is also organized, has its own layout. So the file is organized in pages, and the page is divided in rows, and the rows are actually our real data. The tuples are what we call the rows, and they are the real data, where the data is stored. But the row also has its own design. So the row has a header as well, And what we see we have a lot of information on this header. We'll see here the most important ones that we is for our discussion. And one of them is this thof information. The thof information, it holds where the data starts on the row, where it physically starts on the row, because the header, the Postgres header, one of the things that it keeps track of the news that is inside of the database. The database doesn't really need to store the null. There are mainly two different ways that we can keep the null information on one database. So one of the designs, we just put something inside here. Let's say this is the data that we have. We store a lot of the integer, the strings, and then we keep 1 byte to represent the null inside of the database. So we choose that sequence of characters to represent the null, and whenever we have a null inside of the row, we just place it there. This is one alternative that we can do. Another is we can just have a bitmap, a map of information like Postgres does. So we can tell if we have a new data here, just having a map of information. So we tell to the database, look, in this row, we have, in our example here, we have 3 columns inside of this row, right? So this is the table T here. If we go here, we have 3 columns inside of this row. Right, star from T here. Limit 10, for example. Oh, okay, I need to run inside of the database, not in the bash. So we have 3 rows here. This one can be null. We can either insert something here to represent the null, or we can just have a map of information that tells that this row here has a null on the position on the column number 3. And this is mainly how Postgres does with null. Postgres doesn't really stores the null. It just tells that we have a null and where is the position that we have the null. So we can save space and we can make it to work more performant, more optimal. Well, as we are here, we can use this extension here, page inspect, to inspect inside of the page that we have on Postgres. Let's try to take a look how those here are organized in our database. I can use this get raw page. It will just get the raw information from the page. So it's like no meaningful or useful information for us here, right? But it's needed for other functions in the same extension. So it will be decoded to get, for example, a header of that page. If I get the raw for the same raw page here and ask them to give me what is inside of the header of that page. See, this is what it will show us. There are few information that are important here. One is this lower and another is this upper. They are the lower point and the upper point. But what are those upper point and lower point? If we come back here, not yet, nope, here. See, I said that the Postgres and the line pointers, they grow towards to the center, and the tuples they grow toward to the center as well. So the lower pointer is the position of my last row pointer or line pointer here, and the upper point is the last position for my tuple here. It means that the difference between in bytes, the difference between the upper point and the lower point, it represents the free space that I have inside of this page. So if we come back from this example, I have mainly no free space in this page here. So all of the space from this page is being occupied. So we can check how many pages that we have here. So I've been checked in this table, I have basically six pages, but we can use a nice thing on Postgres that is called CTID. It's a virtual column that all the tables that they have, and the CTID, it holds the page information. So I want, for example, here, in this information, I'm on the page number 0. So the first number here, it represents the page. And the second number here represents exactly the line pointer. This is the line pointer that we have. So on the page 0, line pointer 1, we have this row here. If I want to see how many pages I have, I can just order by CTID desk, right? And limit 1, for example. So we have 6 pages here, because the last one's the page number 6 and line pointer 58. So if we go to that page, oops, and if we go to that page, we'll see that we have a lot of free space, because the upper page here, the upper point is pretty far from the lower point. So I did the math here in the select, just using the upper minus the low. So it does the math by itself. And it says how much free space we have here. So we have a lot of free space inside of the page. And this is how we can inspect the page layout that we have on Postgres. And if we move on, we can also inspect how the rows are stored, how they are organized inside of Postgres. And this is a very nice function here, that it's the heap page items. So what it gives us if we go here? It will give us the header from the heap page. So up to here on this TOID, it's mainly the header that we have inside of that row. And then it also give us the data. This is the binary data that we've been stored. Well, for this discussion here, we are not interested in all of the fields here that we have on the header, but we want to see few of them, because we want to understand how they can impact the data, how the storage can be impacted. So we basically will take a brief overview here on the line pointer. Well, we already saw the line pointer. This is the line, what it represents. The line pointer has this information. This is where the data really starts. This is the offset of the row. So in this example, let me select stuff from theap, limit, let's get smaller, limit 5, for example. I also want the CTID. So here we have on the CTID, on the page 0 and the line pointer 1, we have this row here. This is the information that's being stored here, that is represented by this binary data here. So the thing is, this row, this exactly row here, it will start in this position in bytes inside of this page. And we can really validate this information. We can go back again to, we can go back again here to the file system. Let's just get this information here. Okay, I want to get this here. Let me copy this, and I want to get this. This is what we need for now. And we also need the table ID. Okay, this is the table ID we've got before. So, all right. I guess I already have the table there. Okay, let's go to the bash. If I do a next dump, see what it says here. It says that the line pointer 1 that holds this row here is telling us that the row going to start at this position. And it says that the row, this same row, has the length of 43 bytes. So if I go to this position here, this is the position that I want to go. This is the position that I want to go. And I want to read 43 bytes, not 48. So if we execute this here, what we get is exactly that row. Look, this is we have char, and because this table is not compressed, we can take a pick on the data. So if we try to get something in the middle, let's get line pointer row ID. Where is my select? Okay, I want to get the same select here. But instead of the first page, I want to, I don't know, let's just do a limit 50 here. Right? I need to, so I want to get this row number 56. I'm gonna copy. This is the data that we have on the row number 56. And for the same thing here, if I want to get 51 and 57, all right. Oh, sorry, I want the 56. So this is the position for the row 56. Let me just get it back here. So on the row 56, it starts at this position inside of the page. Oops, not this. It holds 44 bytes, and it starts on this position inside of that page. Let's get to the bash, and if we run here, and that's we get. So we have the row. This is the text information, and this is actually the number 56 in binary, right? I mean in hexadecimal, and this is how Postgres stores a 4 bytes integer inside of the database. So if we do we get a calculator here. Where is my calculator? It seems I cannot get my calculator from here. That's fine. I know I need to go this. If I get my calculator now, if I get the number that we have 38 in hexadecimal, actually it's in hexadecimal, 38, and we move to, this is what we get. We get the value of 56. That is exactly what we were looking for. That is exactly the select 56. Okay, let's move on. The other important information that we have on the header, let's get the header back here again. We want to get here. So the other important information that I want to show you guys here on the header are the masks. So we have two mask columns here on the header, this t-info mask and t-info mask 2. What we see here on the t-info mask 2 is how many rows we have inside of the table. So it holds the information on how many rows we have inside of the tables and some other flags. We will see some of them later. And the t-info max, it also holds a lot of flags here. For example, this last bit, it's a bitmap. So every bit has one meaning. This last bit here, it tells us if we have any new value inside of this row. So as we see, we don't have any new value here in this row because we've been inserted all of new information. We can, for example, do an insert into t-heap values 2001. I want new for the text. Just make sure I can have new. Nope, I cannot have new on the text, so I need to have a text. And then let's get just text, not new. But I can have a new on the last value. So I still gonna have a new here in this. Okay, I'm gonna insert here. And remember, I want to have it on my checkpoint. Let's just make sure we get this information to the disk. And if I just do it where ttid equals what we have here, I can just copy and paste. Oops, I think it's moving too fast. Actually, I want the line pointer because we're already inside of the row. So we want, this is page number 6 because it was inserted in the end. I want all the by one desk limit 5. Okay. Actually, we want this here. Up to the front, right? Yeah, we got it here. All right. What if we got wrong here? Oh, because we want the LP. Nope. What did I? Let me do a select star. Probably the name of column is not correct. All right, limit 1. So, yeah, it was misspelled. There was a R, an extra R here. That was not expected to exist. Cool. Now we have what we need. We just copy and paste. Right. And it's wrong again because it's just redo what I did. Back here. It's back here. And there's an extra select. Now I got it. Order by desk LP. It looks like I don't know how to write that select. That's interesting. Order by. All right, finally I got the select right. So we want the page, but we want this as a desk. Oh, here, this is what we got changed. The last bit, now we have it as to 1. So it means that this information here, it's new now. So this is how those are very important information here. And right, let's move on. All right, we're back here. The next slide is one thing that is important is the page size. The Postgres cannot split the information between different pages. So everything should be inside of the same page. So it means that we have a really large information that needs to be stored. It needs to be stored outside. That's what we call toast in Postgres. For example, if we have one file that we want to store inside of the database, the Postgres cannot store that information on the page inside of the heap file. So what it does, it has an external table it has the same name of the very same heap file, and then it creates a pointer pointing to there, and it stores all the information outside. So TOTS itself deserves a whole talk. We are not going deeper here because they do not really impact what we want to see. And now we are getting to what is important to this topic, padding. Postgres, and actually the CPU, the data inside CPU reads, it needs to be aligned with a certain size. So the CPU alignment, the data alignment, the size of the data alignment makes the CPU works much faster and most efficient when it's going to memory. And because of that, every single data type in Postgres has what we call its natural alignment. The natural alignment on Postgres is by 8 bytes. And it will try to keep the data inside aligned with those 8 bytes. Let's go, for example, here. I'm gonna create here another table that we want to inspect here. Where I call this table Q item. So it's a very simple table. I'm gonna create here. I'm gonna insert 1 million rows inside of this table here. So while we're insert here, if we check the size of this table is not that large. It's just 73 megabytes. But remember that I said every single data has a specific size in Postgres, and they need to be kind of aligned internally. So for example, an integer of 2 bytes, it has 2 bytes. That's why it's an integer of 2 bytes, right, in Postgres. But the Boolean in Postgres, it only occupies 1 byte. A numeric type, also varchar, or those types that can change in value, they do not have a type length, a specific type length, because they can vary in size and length. So what it happens is, because the information needs to be aligned in 8 bytes, every time that Postgres gets, for example, this order in here, that we have one column that has 2 bytes, and another column that has 8 bytes, well, it cannot just place this information after each other, because in the end, the alignment won't be by 8 bytes. It's gonna get 10 bytes here. The same here, we have 1 byte and 8 bytes. So what it means is Postgres will put 6 bytes of zeros here to make it aligned with an 8 byte data type. And it causes a lot of cost. If, for example, if I create the same table, I'm gonna create exactly the same table here. I'm gonna call it item good. What I'm gonna do is I'm gonna reorganize the table based on the type size, the type length. I'm gonna put all the 8 bytes, because this is the alignment size that we have in Postgres, one after each other. I'm gonna put the ones that are multiplied by 2 or 4 bytes, because if I get like 2 columns together of 4 bytes, well, they make a block of 8 bytes, right? So then Postgres can make the benefit of this alignment. And in the end of the table, I'm gonna put those on there. We don't know the size, that they can vary the size. And this is exactly the same table. So I'm gonna drop if it exists, and I'm gonna create using the select from the table Q, because I want exactly the same data. So I don't want anything different. And I'm gonna do a vacuum here, because I want this to be updated, and a checkpoint. If we check the size from those tables, look what we get. Just because we changed the alignment of the rows, we get 20% improvement in the space. That's a lot. And that's how we can benefit from changing our model, not really changing, creating new or older tables or different tables or changing the relationships. We can just change the order of the columns inside of the table, and we can get this huge expressive gain here. And this translates in performance, because everything that is inside stored on disk, it goes to memory. And so what we just did, this is just an overview of what we did. So we created a normal table. We saw that the table was huge, right? It was of 73 megabytes. After just changing some order, what we got is bad, 20% of size gain improvement, right? And remember that I said that Postgres, it doesn't really remove the rows inside of the table. So because of that, Postgres needs to keep track of how those information are stored on the table, right? How it can clean, or what it needs to be cleaned on inside of the table. To keep track of that, Postgres has what we call the free space map. So the free space map is just a map that tracks what need to be cleaned or not inside of Postgres. And one of the benefits that we have of this kind of thing is, if we have one change, if we change the information, an update, and it doesn't change the row from one page to another, let's go back here to be able. Remember that I said here, when we update the item here, it creates a new tuple, right? So if it is still inside of the same page, we don't need to change here the new address. So we don't need to change the index there. So because of that, we have this performance improvement. Still, Postgres needs to keep track of that information. So it has a map, a free space map, to keep track of that space that's free and needs to be cleaned. And how this free space map works? Well, it's a very simple map. It's that it has a B tree. It's another file that has a B tree. In this file, it gets all the rows that we have. So all the pages that we have. If we have 1,000 pages inside of the file, we're gonna have 1,000 entries here. And because we have one page, one entry here per page, it can get very large, right? So this is another benefit of having the table to be smaller. If we reorganize the data types to get the table from 76 to 50 megabytes, now we have much less pages inside of that table. So because we have much less pages inside of that table, that file, we have much less entry here. And the work that needs to be done to find which the space or that needs to be cleaned, or where we can insert or we can put a new row inside of the Postgres, now gonna be smaller as well. So all the operations from the Postgres are now speed up. Everything that has a gain, just because we reorganize it, we change the organization of those rows inside of the Postgres. This is an overview how the free space map works. And well, yeah, we're coming to the end. We are in the last minute here. I needed to make it speed up a little bit in the end, otherwise we won't be able to make everything here. And the summary, guys, is that what we saw here, we can get a really huge benefit from Postgres when we just change that order of the rows to make it aligned with the byte size that Postgres use for the CPU. So make the alignment possible inside of our table can make a huge difference from cost perspective, from performance perspective and for the overall maintenance of the Postgres. And so in the end, we don't really need to change the data model. We just need to reorganize it. Well, that's it. I hope you guys have enjoyed. And if you have questions, you can drop me a message on my email. This is my email. You can find me on LinkedIn. This presentation and all my scripts will be here on my GitHub as well. And I'll keep here on for a couple of minutes to answer any questions. Well, thanks, guys, for your time. Yeah. I'm reading now here the questions. Oh, a lot of directions. We'll see here. Yes, we will have a recording for the sessions later. All the talks are being recorded. Oh, the idea I'm using here, let me get my screen share again here. I'm using Visual Studio Code. This is Visual Studio Code. This is a plain PSQL. I just got some keys here that I can execute on everything here. So this is a plain PSQL. There's nothing fancy. I have few bashing sessions here underneath, so I can switch them easily, and that's it. PSQL Visual Studio Code, it has a few plugins for Postgres and other database, but I've tried a couple of them. I didn't feel comfortable using them, so I'm just using the old plain PSQL here to execute the queries. Yeah, Fabrizio, you're right. This is Visual Studio Code. Yeah, sure. Let me get from the slide. Just a second, asking if I can share the GitHub. All right, this is the GitHub. I'll create a new project there and call it PL21. So I'm gonna put all the information there. Fabrizio, if I did some benchmark, yeah, I did some benchmark that I'm still working on those. I'm gonna have a blog post that I'm probably gonna finish by end of this month. And my initial benchmarks is it depends on the table, right? So I try to use this table here because it's sort of a real representation of what we could have on real database. I didn't want to use a lame table, and if we get numbers, integers, numeric values, I mean, the gain can be huge. I've got more than 30-40% gain in when we have, for example, int q altogether with int 4 and int 8. When they are mixed up, the gain is much larger when we have varchar, especially if those varchars, they go for toast, because on the table, you only have the pointer to the toast. So, but when we have numerical columns and they are mixed up, the alignment, then they are mixed up, we can have a really huge gain in the storage. And another thing that I'm experimenting is how this storage gain can be translated to performance gain in terms of memory. For example, because as the Postgres reads the block, the whole block to memory, so if we can put more information inside of the block, we can have more data in our memory, right? So the memory is going to be more efficient used. Also, the time to parse or to read all those information from the CPU, they can drop. So my initial finds is we can get around 15% gain in performance if we can get up to optimal with the best alignment that we can have. But I'm still doing some experiments, so I'm going to write a blog post, and I'm intending to finish them by the end of this month, and I'll try to share all those benchmarks and things. Well, Mohan, I didn't get to UID yet. So this is something that I also want to track, because UID can gives us another whole talk, right? Because there are a lot of benefits and drawbacks with UID. And other database like that use cluster index, for example, they are pretty horrible when we use UID for the key identifier, for example, as primary key, because they stores the primary key in all or secondary keys. Well, from this perspective, Postgres doesn't have a problem, but I'm still going to see the representation of how the UID is being represented inside of the table itself. So I still didn't get to testing UID. I'm still testing the numerical columns to go there. But, well, honestly, I don't know. I don't have answers for you right now. So, but they are on my roadmap to put on the blog post. So you can find find us on the Percona's blog I gonna share by the end of this month. Well, if you guys have more questions left, well, let me check the QA here. Well, yeah. Well, thanks, guys. Thanks again. Let me leave my information here again if you want to quote. So you can always drop me an email on my email here. We can also find me on LinkedIn. I'm usually not that present on social medias. I'm trying to get up to. Well, you know, a lot of them are blocked in China, like Twitter, Facebook, so I don't use them frequently. So that's why you don't frequently see on social medias. But you can always drop me an email. You know, you also can also find me on LinkedIn. I'm pretty frequent on LinkedIn there, and if you have questions and anything else, you can. I'll be there. And thanks for being here and sharing this time. That was a pleasure. Thanks, guys.